All right, last time we had started to investigate electromagnetic induction. We discussed, we first looked at a sort of a traditional way to envision why electromagnetic induction occurs, and then we transitioned to developing methods that allow us to understand how electromagnetic induction occurs in really any situation, because that traditional method that I had originally shown is very difficult to when you have more complicated situations. Thank you, Java. I know you have an update. You tell me that every 10 minutes. All right. So Lenz's law was a conceptual law that helps you understand the direction of the induced current. There is a second law called Faraday's law, which goes over how we attach a number to these things. This is the more mathematical side of it. And the law is actually quite simple. It's sort of profound in a lot of ways, but the Faraday's law says that the EMF, meaning the potential difference that is generated, is equal to the absolute value of the change in magnetic flux. Very powerful statement. There's a lot going on with it. It looks simple. There's a lot going on with it, though. The absolute value that's there is to ensure that the value is always positive, because we want to assign directions of current by Lenz's law. So that's the only reason why the absolute value is there. Now, when you look at this derivative here, remember that magnetic flux is a function, well, it's really a function of three things. I'm going to say two, though. It's the magnetic field and cross-sectional area, which is the A cosine theta. So there's actually two aspects to magnetic flux, and so when you consider the derivative here, you have to consider that both things, right, or one of them is going to contribute to that. I mean, look, if you have, let me draw this up here, your magnetic flux is, say, we'll just say it's B, A, where A is this cross-sectional area here, and you want to take the time derivative of that. What's going on here? Then you have a B dA dt. We got a chain rule. Is it called chain rule? I don't remember the name of these things. Chain rule, product rule, yeah, product rule, not chain rule. I know my terminology. So you actually have two terms there, really. The area through which the magnetic field goes through, if that changes in any way, that contributes to the EMF. And if the magnetic field strength itself changes. So there's both things that can happen here. And so the challenge we have is, can you properly express these things? Now, the change in magnetic flux, the change in magnetic field is pretty easy to do. It's this change in area that can be a little tricky. All right, a little tricky. So let's go ahead and apply it to the original problem that we did in the last lecture, where we have a magnetic field that runs into the page. We have this conducting thing, wire, whatever, on a rail. It's pushed to the right. And in terms of magnetic flux, the magnetic flux is increasing here because the area is, not because of anything that's going on with the magnetic field. So that change in the magnetic field part of that product rule is not really something we're interested in. But here, if we want to express what the magnetic flux is, it's A times B, but A is increasing. So we actually want to express that as an area in terms of dimensions. So the one dimension's L, and that's locked into place, and then it's X that increases. So we can state that the area is x times L, some rectangular area. So I'm going to put this into my formula down here. So I have the magnetic flux is XLB, and I'm going to take the time derivative of that. Well, L doesn't change and B doesn't change. X does change. In fact, if we put the X with the time derivative, we see that's just the velocity. So this is VLB, which is the result we got previously. And if we want another current, we'd have to be able to specify what the resistance is in the wire. So that's the same result we got before. Now we're thinking about this in terms of magnetic flux, and it's pretty straightforward when we think about it that way. So that's great. I have a question for you. The induced EMF around this loop is what? Now, the loop is fixed, but the magnetic field is increasing. So let me know what you think about that. That's a good question. Uh-oh. I don't know. I don't know, people. Walter, your first answer is probably, the best one. David, I'm liking E quite a bit. All of you like B. I don't think so. It is E. Now, if you said B, you did something right. You figured out the slope of the line. Slope of the line is 50. So that would be a dB dt of 50 Tesla per second. But you're not done. You'll need to multiply that by the area to get what the change in the flux is. So multiplying by the area gives you the 0.02 volts. All right, let's do the first example here where we actually can put some numbers behind this stuff. All right, let's look at it. This is good stuff. All right. Oh, I forgot. Let's go back. Sorry. Let's go back. This loop here. Okay, which direction is the current? Let's review. Our magnetic field is out of the page and increasing. Step 1. We want to oppose that change. So we want an into the page magnetic field, which would be that's part 2, which would be accomplished by having a clockwise current. So those are the 3 steps. Number 1 again. Increasing magnetic flux out of the page. To oppose it, we want an into the page magnetic field. A clockwise current will do it. 1, 2, 3. Okay, hope that's clear. Well, let's now look at the example. All right, so we have this rectangular loop here that is being pushed into a magnetic field. The magnetic field only exists in the space that you see here. And as a result of that, the magnetic flux is changing because the effective area where the magnetic field is increasing. So when we do these problems, we always do them in 2 steps. Let's look at Lenz's law first to determine what the direction of the current is going to be. Step 1, the magnetic field is increasing and out of the page. Step 2, we want to oppose that, so we want an into the page magnetic field. A clockwise current will do it, just like in the previous example. So we established that we need a clockwise induced current here. Now we need to use Faraday's law to determine what the EMF is going to be. So we do EMF is the rate of change in time of the magnetic flux. That is A times B. There's no cosine factor or anything to worry about here because everything's perpendicular. Or, yeah, wait, parallel, not perpendicular. The B is constant. The magnetic field's constant, comes out of the derivative, and so this is just dA dt. So we have to be able to specify the rate of change in the area. Well, what's the area? The area is going to be given by y times L. L is this length here that will not change. And y is simply the distance that the loop is in the magnetic field. And y will be increasing as this thing goes up. So I'll specify this as y times L. The L is constant, it comes out, dy dt becomes v. So I have all the numbers that I need here. If I want to know what the current is, then I'll have to divide the EMF by R, the resistance. I'm told the total resistance of the loop is 0.1 ohms. So I got all my numbers here. Magnetic field of 0.2 Tesla, speed of 50 meters per second. The length here, you got to put in meters, 0.05. And the resistance is 0.1. And we get a cozy 5 amp current as this thing is being pushed up. And it will stay that way until the bottom portion gets into the field. And then the flux no longer changes and there won't be a current anymore. Okay, so the current only happens when the magnetic flux is changing. Once the loop is fully in the field, no more changes happening, so there's no more current. Any questions about this problem? Is this clear?
Professor, could you explain why the current's clockwise?
Yeah, so for Lenz's law, the first step is to realize that the magnetic flux here is increasing and the magnetic field is out of the page. We want to oppose that, so that means we have to have a magnetic field that goes into the page to oppose the increase. So you use your thumb for your magnetic field, and when you rotate your right hand, it goes clockwise. So clockwise induced current will produce the into the page magnetic field. All right, the square loop shown here, which looks more like a diamond, but it's a square, just a little tilted, right? Moves into a 0.8 Tesla magnetic field at a constant speed of 10 meters per second. The loop has a resistance of 0.1 ohms and enters the field. We want to find the induced current in the loop as a function of time. Okay, so the magnetic field does not change, but the effective area that the magnetic field in does start to increase. So we do have a current that will be induced here. And we can talk about Lenz's law right now. So the magnetic field is into the page, and it will be increasing in the area of the loop. Into the page, the magnetic field will be increasing. We want to oppose that change, so we want an out of the page magnetic field, which is accomplished if you do the right-handed rule. Thumb is out of the page. You curl your fingers counterclockwise, and that will be the direction of the current. Now, this problem is a little bit harder for a couple of reasons. One, the geometry is a little different. We'll see that in a minute here. But also, the rate at which the area increases is not a constant. It's not a constant here, actually. Because as you push this into the magnetic field, you include more and more of an area that's basically a triangle. And the rate at which that area increases will go up and up and up until you get to the middle. That reaches the maximum. Let's look at how this is done. Now, there's a lot going on this slide here. Let me just walk you through it very carefully. Lenz's law is stated right up here. So this is our Lenz's law stuff. I'll put a nice pretty pink box around it. And this is what I discussed previously. We have a counterclockwise induced current. I got 3 stars with the 3 things you have to think about. Now, let's think about what happens when we enter the magnetic field here. When we enter the magnetic field, there is effectively a triangle of area here because we put the corner into the field. And I know the magnetic field doesn't change, only the area changes, so I'll need to be able to figure out a way to express what the area is in terms of the dimensions here. So what I decided to do is to investigate one of the triangles, and I'll highlight this in this pleasant, really light blue. It's lovely light blue. I really am a big fan of this blue, actually. But this triangle here, and I'm gonna figure out the area of this triangle, and I'm gonna double it. I mean, I could just figure out the area of the whole triangle too, but whatever. 2 times the area of a triangle, 1/2, and I put a coordinate system right here to specify how I would state coordinates. So basically, the coordinate system is put right at the boundary here. Y goes up and down, obviously x is left to right. So I decided my coordinate system will have an origin right at the boundary. So after the corner enters, I can easily specify what the dimensions of the triangle is, because the height is y and the base is x. So it's 1/2 xy for the area. And again, I'm going to double it. Now, this is a square. And that means the angle here is 45 degrees. That means x and y are the same. So I'm just going to specify this as being x squared. The 2's cancel out, and I replace y with x, and I get the area as being x squared. Now I need to relate that to the speed somehow, so I just use simple, rate times time equals distance. So I replace x with vt, and that is how I'm going to specify my area. Not the only way to do it, but a good way to do it. I like this way. So let's do Faraday's law now. Now that I have specified my area at any given moment in time, I can now work out the derivative here. So I have my change in magnetic flux, right, with time. I replace that with BA. B comes out because it's constant. I put in my values for what A are. A is. And taking the derivative of that, well, the V squared comes out because it's constant. And then the T squared becomes 2T. And so now I have this formula down here, 2B V squared times T. Now this is what I was talking about earlier. The EMF is a function of time, and it increases as time goes on. And the reason why is because the area has this steadily increasing rate to it. The area doesn't increase at a constant rate. It goes up as a squared factor. I mean, look, there's a squared factor here, right? That's a quadratic factor. So that means the time derivative is going to be a linear function. This is a linear function here. Anyway, I got to figure out what the current is. So I'm going to divide this by R. I'm told that the loop has a resistance of 0.1. And so putting that in here and putting all my numbers in reveals... so I got 2.8 is my magnetic field. 10 is the speed. Now, the... what did I do at the time here? Oh, anyway, that expression is just what the current is, but I want to know the max current. The max current occurs when half the loop is in. Half the loop is in. Because that's the greatest rate of increase in area. And then what happens is after that enters, then your area is still increasing, but now the rate at which it increases starts to decrease. Again, this is a lot of calculus here. And so I need to basically just figure out at what time is half of this loop in there. And so I worked that out down here. That distance is going to be 0.1 over radical 2. That's, again, because it's the base of a 45-45 triangle. The hypotenuse is 10 centimeters. So the base is going to be that divided by radical 2. That gives me a time of 7 milliseconds, apparently. So I put that 7 milliseconds here. You got to make it SI, though. Okay, I put 7. This is 707. It's a few more decimal places out. Anyway, work all this out. I get 11 amps is the max. And it says something about give a graph. Well, you can't really give your graph until the end of it. But what happens is your current will be gradually increasing until you get to that 7 milliseconds, and then it's going to gradually decrease. Okay, so there's still a current, still an EMF, but the rate at which the current increases is in the first half, and then it decreases in the second half. And again, it's because when you're halfway through, the rate at which the area well, now the rate at which the area changes is a decrease in amount. It's a linear factor. All right, that's a pretty hard problem here, but this really all comes down to just being able to specify what the area is. Really, I mean, that's when you look at it, a lot of these things aren't too challenging, but specifying the area is a bit complicated, actually. All right, so you know what? We want answers right now. We want answers. Because, look, let's go back here, right? Where do I want? Okay, look at this. We in here, right? I push this rod over to the right, and there's a current. Okay. Now that you can see clearly what's happening here, you have an area that changes. So that makes it really clear that there's a separation of charge on the wire here, and then that pushes through the current. There's an electric field established. But what if there wasn't any wire here? What if we just changed, we had just a space where there was a magnetic field, and we started to change the magnetic field in that space? According to Faraday's law, there would be some kind of electric field generated. Well, that is true. So ultimately, really the question is, you know, in order to push a current through, you have to have an electric field, right? I mean, that's the core of what happens in circuits and current, is ultimately there's an electric field established. So in this example here, we have a conducting loop, and we have a magnetic field that increases into the page here. Well, we want to, if I'm thinking about Lenz's law, that's going to create a counterclockwise current to oppose that change. And that means there's an electric field here that has this sort of circular nature to it, much like magnetic fields look like. And you know what? If there's no battery, there's nothing else here, I mean, the question is, where in the heck is this coming from? Where is the electric field coming from? And the answer is that it is created. It's an induced electric field. So we've been saying induced current. We're saying this is an induced electric field. And it's the space. The entire space surrounding this has an induced electric field. And whether we put a wire there or not, there's going to be an electric field there. So that seems kind of wild, but ultimately what we're saying here is that you don't need to have a conducting piece there for an electric field to be generated. It's generated by virtue of the fact that the magnetic field exists and changes, and that creates the electric field. Which is a little wild when you think about it, because when we introduced magnetism, that's effectively what we were saying, is that the magnetic field is created by the motion of charge. If a charge moves, then the electric field in the area changes, right? In a given spot, the electric field is going to undergo a change because the particle moves. And then we said that brought about this magnetic field. And it's not surprising that the opposite is true, and it is true here. Okay. Now, this leads us to a sort of interesting form of Faraday's law. We actually can enhance Faraday's law by identifying that the EMF here is going to be related to the electric field ultimately. I mean, we were saying before the rate and change of, yeah, it's, you wait. There's a lecture coming up where I'm going to tell you that there is no electric or magnetic field. It's just the same field, just seen from different reference frames. So it's weird, but yeah, there really is no electric field and there's no magnetic field. It is one field called electromagnetism. And what you see is based on your initial frame of reference. So, yeah. In fact, yeah, I've been lying to you, basically. Yes, I have been lying to you, but it's for your own good that I'm lying to you. Because I'm not going to introduce the fact that electromagnetic fields don't exist independently without you understanding a whole lot of other things. So anyway, we're identifying here that the EMF, based on the definition of what potential is, it's the work done on the charges over the charges. And if we relate that back to the statements we had earlier, we have this path integral here. Now, you've seen this already. This is not new here. When we introduced the relationship between potential and field, we came up with this. There was a negative sign here, but we don't have the negative sign here because, again, that's going to be part of using Lenz's law to do that. So now we can join these two things up. The EMF, we can relate that to the electric field. And so now we have this crazy relationship here that tells us that the change in a magnetic field induces an electric field. So the right side is what we've been describing as Faraday's law. And if we are just thinking about the change in the magnetic field, we can write our Faraday's law to look like this. And again, E dot ds is just potential. That's all that is. This is not a complete Faraday's law because you can have A change too. And you'll see that a little bit later here. Anyway, just to forward with that, I mean, the progression you take in physics is you do this, okay, and we have another lecture to go, and then you can branch off. And part of the branch off is to look at AC circuits. And we just kind of tease that subject. It's like, we'll look at that for a couple lectures. And then we're going to pull back and say, engineering's kind of lame. You want a job and make money, whatever. But we want to see the cool stuff. So we pull back and we go to the other branch. The other branch is electromagnetic waves. And then the very next topic is special relativity. So, in fact, special relativity, this whole stuff here ushered in special relativity. So if you are, after we do this lecture, I mean, the lecture I'm going to have that's kind of wild is the one that's going to be on 2 weeks from today. But anyway, if you're interested, and I highly recommend it, if you go to my webpage and you go into my 211 class, I have 3 lectures on relativity. So if you really want to learn some relativity, and you got about, 5 hours of time to just sit back and listen to my soothing voice, talk about relativity. The 230 person, isn't that, you talking about Professor Alvarado? There's no summer anything. I don't think there's summer. I don't think there's anything going on in summer. Oh, Jose, okay. I don't think he's new. No, he's been around for 10 years, I think. He's adjunct. He's not new. We do have we keep hiring these new people. They kind of show up and they disappear. We've had a lot of people. We haven't had a solid circuit analysis person in a while, which is strange, but whatever. Okay. Anyway, I don't like AC circuits. I don't like electrical engineering. I like my head in the clouds. Okay, let's keep going though. No, he's definitely been around a while. I know that. I'm evaluating him this semester. I know he's been around at least 9 years, 10 years, something like that. So, anyway. All right, so, this is what I already said. All right, now let's look at another perspective of this here. Trying to understand what's going on in these solenoids here. When you have a magnetic field, right, as a result of the current going through, if you start to change that current, That means your magnetic flux is going to start to change, which means you're going to produce an induced field here. In addition to the field that already exists that's pushing the current through. And this is a very important element of things we're going to be talking about, I think, in the next lecture called inductors, which is exactly this principle here. The change of magnetic flux to the solenoid creates what we call a back EMF, an EMF that exists across the solenoid that acts as basically a resistive element. Or if the current is decreasing, that actually will encourage more current. And so it could be a resistive element, or it can be a source of potential, actually. Actually can drive current. So we'll see the details of that a little bit later, though. All right. So these induced electric fields have a circular nature to them for magnetic fields that are straight, like this. We also saw this for, right? This is the same thing for electric fields. The charge is moving in an area of space, the magnetic field is circular around it. Well, the same thing applies here. Okay. Well, we can actually figure out what these electric fields are. Let's just take a really simple circular loop. If we do a circular loop, then the electric field at a given location from the center is going to be constant, right? There's going to be some symmetry here. So you can take the E out of the integral, and the path length is just the circumference of the circle here. So that's going to be 2 pi r E. We set that equal to A dB dt. A is given by pi r squared. We solve for E, and we have this nice expression here. This is what the electric field is along this loop because of a changing magnetic field in the space that's here. This is a specific example, by the way. This only applies when your area is constant and the magnetic field changes in an area of space here. So if you could specify what the change in the magnetic field is here, at any distance from the center, you could specify what the electric field is, which is a little wild because this is a linear function. It means when you're very close to the center, the field is not so great. As you get farther and farther and farther away, the electric field actually increases. It may seem astonishing that it increases, but it can only increase in the space where the magnetic field is changing. So while it might seem amazing, like, oh, a mile away I can have a huge electric field, well, if you can manage to have a magnetic field that changes in the space that encompasses an entire mile, then yeah, but that's not something that's easy to do. So, okay, so question for you here. The magnetic field in the picture is out of the page and it's decreasing. So what is the induced field going to look like here? I'm thinking B looks okay to me. Let's think about it though. Decreasing out of the page, we want to oppose the change. Therefore, we also want a induced magnetic field that is out of the page. And I curl my fingers on my right hand, and I have a counterclockwise loop here. So the answer is B. Okay. So that's the direction the current would go, but now we can also say that's the direction of the electric field in this space, whether there is a wire there or not. Okay, so this down here becomes now our formal Faraday's law that encompasses everything we've been talking about here. So the EMF, we specify this in terms of electric field. We can now drop the absolute value. We're sticking a negative sign in front. That's basically a statement of, well, it's a statement of several things here. I mean, it ultimately does come from our integral of electric field and potential, and that the direction of the electric field is the direction towards lower potential, So we're going to put that negative back in here, and then the derivative is the same thing now. It's the magnetic flux here. So this is the complete Faraday's law now. Of course, well, while this is the complete Faraday's law, we don't typically look at it from this standpoint, but we typically are going to look at it the way we've earlier discussed it. And then the only other situation where there's like a thing in space would be this equation down here. We're not going to take it any further than that because it gets pretty complicated after this. You start getting into some really wild calculus and linear algebra if you keep going with this. But anyway. All right, let's do a problem. The magnetic field in the figure is decreasing at the rate of 0.1 Tesla per second. What is the acceleration, magnitude, and direction of a proton initially at rest at points A to D? Okay, so the logic here is this. If the magnetic field is changing, we are going to generate an electric field. The electric field will apply a force to the proton and cause an acceleration. So we first have to figure out what the electric fields are first, right? We first have to figure out what the electric fields are first. Let's do it. Let's do it. All right, so our expression that we derived earlier is that the electric field is equal to R over 2 dB dt. Okay? Now, we can write, I guess I'm going to do everything in one go here, looks like, according to my notes. The force on the proton is given by QE, and if that's the only force that acts upon it, that's equal to MA. So we solve for E and we get MA over Q, where Q is the fundamental charge. So I'm going to plug that in for E over here. I'm going to rearrange everything to solve for A, and I get this nice expression here, RQ over 2m dB dt. This gives my acceleration. So the acceleration now just becomes a function of the distance, right? That's it. Now B is in the center, so R is 0, and the acceleration is 0. So that's my first statement there. Now, point A and point C are at the same distance from the center. So they're going to have the exact same magnitudes for the acceleration, obviously different directions. So I plug in all my numbers for a radius of 1 centimeter, and we get 4.8 times 10 to the 4 meters per second squared. You would double this to get D, because D is twice the distance. So double in that number, 9.6 or whatever that is, times 10 to the 4 meters per second squared. In terms of directions, the field is decreasing and it is into the page. So we want to oppose that. So we also want a field that's into the page. And so this produces a clockwise current. That means on the left-hand side, the electric fields point upward, and therefore the accelerations point upward. And on the right-hand side, the electric fields point downward, and therefore the accelerations point downward. So this equation, R over 2 dB dt, can be applied to any region of space where magnetic field changes. Okay? As long as there's no actual loops there, we're not considering a different area involved, you can stick with this thing here. If area ever changes, though, can't use this. But I can't think of a situation that we're going to encounter where that happens. All right, so let's keep going. Are we doing on time? Well, okay. Now, well, we just established that a change in magnetic field is going to produce a circular electric field. What if we were to take just empty space that has an electric field in it, and we change the electric field? For example, say we have capacitor plates, and we start to increase the voltage on the capacitor plates. Well, that will change the electric field on the inside. So if you gradually increase the voltage of the capacitor plates, you're increasing the electric field in the region between them, And guess what happens? You have an induced magnetic field that is also circular. The same things apply there. Okay, and so what's wild about this is the following. You know, the changes in one field produce changes in another field. And these things influence each other. And this led James Clerk Maxwell, which Maxwell's equations are named after, to come up with a lot of ideas behind how these are working. And one of the things that ultimately came from this was the idea that changes in, say, an electric field will create a magnetic field. So if we change that electric field, we can change the magnetic field, but the magnetic field produces change in the electric field. So you basically have this oscillatory behavior between the two fields. If you have a region of space where you have change in electric fields or change in magnetic fields or both, that automatically generates changes in other fields. And that's the property of waves. And so we're going to look at this after we do AC stuff, because we have another lecture on inductors. Then we get into a little AC, then we get back into this. But ultimately, this, you can model the changes that occur here as a wave. And we're not going to get into this because we haven't really covered waves. Waves are something that we cover in Physics 211. But when you start to look at the changes in the waves and model them as wave functions, and you work out the speed of the wave is given by 1 over radical E naught mu naught, where E naught is the electric field, the Coulomb's law constant in here, and the mu naught is the Biot-Savart law constant. And these are both involved in the speed of this wave, which, by the way, is the speed of light, which is crazy because the things we've been talking about don't necessarily involve light, but apparently they do. In fact, any changes to a magnetic field or electric field or electromagnetic field, any alterations to the field propagate through space as a wave, and those waves are called photons. So any photon of light, any photon, any light at all, is the consequence of a change in electromagnetic field. I mean, that's exactly, if you're thinking about, like, a radio tower, okay? In a radio tower, transmitting radio waves over the air is simply done by taking charges in the antennas and have them oscillate. And that oscillation produces electromagnetic waves, which cause other things to oscillate in the same manner, and that's, those are all photons. And that's ultimately what we're talking about when we're talking about transmitting that information. So it's getting weird. All right, now, seemingly unrelated topic. Sort of is, sort of not. But we're going to wrap up this lecture with kind of a miscellaneous topic that I got to cover that really doesn't fit anywhere else, but just here. Yes, because we've kind of talked a little bit about generators and things like that. And it does involve electromagnetic induction. Is the idea of transformers. And so a transformer is a device. Why do I have a generator here? I guess generators are related to this, right? Okay. I don't know. Generators, yeah, why is the generator stuff here? I thought I was talking about transformers. Well, anyway, let's talk about the generator, I guess. I thought I was talking about transformers. Anyway. So here, I'll show you this example here. This is a real simple way to envision how a generator works by converting mechanical energy into electric energy. What we have here is we have a conducting loop. We have 2 permanent magnets here, and we let the loop rotate. So something mechanical will rotate the loop, okay? And what that means is the flux changes because the effective area changes. It's that cosine factor. So it's one of those wild examples where the cosine actually matters here. And so you can see the way this is conducted down here. You have these rings that allow the rotation to occur, but you still keep in contact with a circuit, and a current gets generated here as a result of the current being generated up here, right? The current just follows its way through, and then it can be put into some kind of electrical energy. The way that we specify that, though, is the d flux dt. The A and the B are constant, but it's the cosine that's changing, right? So the cosine can be specified as an angular frequency, so cosine omega t. Take the derivative of that, and we get a sine function. So this represents what our EMF is, which is the basis for AC circuits. I mean, this is going to generate an alternating current here as this thing spins, as it, because as it starts to, as it starts to get more aligned with the magnetic field, the current should be going down. As it turns more, the current starts to go back up. So the current's constantly going down, up, as this thing spins, and it follows a sinusoidal function. Okay, so this is what I thought I was talking about: transformers. Transformers use electromagnetic induction to step up or step down voltages in things. There's a lot of situations where you want to be able to either transmit power or apply different voltages to things, and you want to be able to transform a voltage from one to the next. And that's the way that's done is through a device like this, where we have some kind of alternating current here at some peak voltage, and if we vary that, that's going to produce a change in a secondary coil that's out here. So this will have a magnetic field that changes, but because this is in a place that's nearby, and this iron core helps to reinforce the field in its sort of circular nature here, that generates a current in the secondary coil here. And so one real common example of that is, you see transformers all the time when you drive around town and you see telephone poles. You typically see them like at transformer stations. You have these big devices like this, but if you go by and you look at telephone poles, you'll see these trash can looking containers. A lot of those are transformers effectively. And the idea is that the wires that transfer the electricity are at extremely high voltages, very low currents. Extremely high voltages to ensure very little loss in the amount of energy being delivered. Having high currents can be very difficult to transmit long distances. But the problem is that if the electrical wires are in kilovolts, you want to be able to bring that to a residential house. You can't have thousands of volts going into a residential house, so we have transformers that step down the voltage to something that works for the house. And it really depends on how many loops you have here. The more loops you have, the stronger the magnetic flux can be. And there's a simple proportion that relates these two together. The ratio of the voltage over the number of turns. This ultimately comes from Faraday's law. Let me write it out here. Faraday's law, EMF equals, right, the change in flux over the change in time. Well, the change in flux that's happening here would be the same change in flux as over here, assuming that the field can transmit through properly. And so this has some EMF based on that, but each loop contributes to the flux. So you have a factor of n here. I'm going to call it n1. That represents each loop and how each loop can contribute to the flux here. Okay, so this d flux dt is the same in both coils. So we have a ratio of basically the EMF, this is number, over the number of turns. And you can adjust the input, you can adjust the secondary voltage, the output voltage, by changing the amount of, the number of coils you have here. So let's do an example of this, actually. So in this example here, we have electricity distributed. No, I don't know. From electrical substations to neighborhoods at 1.6 times 10 to the 4 volts. Woo! It's not oscillating voltage, which is not really important for this, other than it will ensure that the transformers work. 'Cause it only works with AC stuff. You have to have a change, right? If it's just DC, that's no change going on there. You got to step down the voltage to 120. So how many turns does the primary coil in the transformer have if the secondary coil is 150 turns? All right, so the relationship we're going to have here is that V2, that's our secondary coil, is going to be equal to the number of turns in the secondary coil divided by the number of turns in the primary coil times whatever the input voltage is. So I'll put my numbers in here. I need 120 volts out of this. I have 150 turns in the secondary coil. You can see that the number of turns in the primary has got to be pretty big to step down the 1.6 times 10 to the 4 volts. You solve for N1 here, and you get 20,000. So the primary transformer has got to be 20,000 turns. The secondary's got to be 150, and that allows things to be stepped down. Okay, this makes sense when you think about the number of turns, right? Because each turn contributes to flux. Having less turns will produce less EMF. So this makes sense. That's 20,000. My pen is just messing up a lot right now. Okay, we want to know what the current's going to be in these things. And one thing that's true about these transformers is that assuming that these transformers operate ideally or close to being ideal, the power that you put in has got to equal the power that comes out. That's the idea. And power is specified by a lot of ways, but the easiest way to do it is to say I times V. We've discussed that previously. That's one of the expressions we had for power. So I put in my numbers here. I don't know what I1 is. That's what I'm looking for, right? V1 is a whopping 16 times 10 to the 4 volts. Current, 260 amps. Woo! Don't touch that. 120 volts. Solving for I1 gives you, I worked it out, right? Somewhere. I don't have a slide for this right now. I got to make one. 1.95 amps. So that's really the current going on in those. I mean, assuming that this is, I don't really know what the, I know it's kilovolts in the power lines, but I don't really know the exact value. But this is definitely an appropriate value here for the current. The current's low and the voltage is high. Okay, it makes the power lines dangerous, but you ensure very little loss, actually.